Hi all, this is Math 2250. I am going to give a lecture that you should listen to on Wednesday, October 27th. It is a very short lecture. It's about the end of section 3.3. It's about the relationship between determinants and vector geometry. So let's get started. Okay, so I want to talk about the relationship of determinants to geometry. And let's consider a pair of vectors in the plane R2. We can always translate vectors so their tail is at the origin. So suppose this vector points to the point AB, and the other vector points to the point CD. So we can say, let's say we have the one vector, let's call it V, is the column vector AB, and the other vector W is CD. These are the components of the vectors V and W. And so the vectors V and W determine a parallelogram, which looks like this, where the point, the only unnamed vertex is the point A plus C, B plus D, as you can see by doing vector addition. And so the main statement I want to make is, let's call this a theorem, is the area of the parallelogram determined by the vectors V and W is the absolute value of the determinant of the matrix given by putting V and W into the matrix, the 2x2 matrix A, B, C, D. In other words, it's absolute value of AD minus BC. Okay, so I'm going to sketch the proof. So the first case to consider is when the vector V lies on the x-axis, that if V has components A and 0. So in that case, the picture looks like the following. So we have the vector A0 with the vector that points to the point CD. And this point would be A plus C comma D. Okay, so what is the area of a parallelogram? It's base times height. Length of the base is, now I put the vector in the first quadrant, but the vector could be pointing in the second quadrant. So the number A could be negative. So the base has length absolute value of A, depending upon what quadrant it lives in. And the height is the height of the vector. The height is D, or I should write absolute value of D. And we can write this as the absolute value of A times D. But that's the same thing as the absolute value of the determinant of what you get by sticking in the vectors into this 2x2 matrix. It would be A, 0, B, D, C, D. Oops, that should be a C. Because the determinant of that matrix is A times D. So this checks out in that case. That's the case where the first vector points on the x-axis. Okay, so let me go to the general case. And the general case is like this. So the general case is, so this would be case 2. So case 2 is the general one. And how does that work? Well, let's look at the picture again. So we have the first vector v, which makes an angle, say, theta with the x-axis. That's v, which has components a, which is given by ab. And then we have w. Now, we can rotate the vectors by minus theta. We can perform a rotation by minus theta. That won't change the determinant if we just do a rigid rotation of the parallelogram, so that this gives a parallelogram which sits on the x-axis. But what are the components of the vectors of the parallelogram? Well, it's not hard to do by trigonometry. We can actually figure this out when we perform this. The coordinates of this point turn out to be, well, it has to be the same length as our vectors, so it's got to be square root of a squared plus b squared and 0. And when we rotate the w vector, well, you can compute what happens to that. So w gets rotated to the vector, and this is again a bit of trigonometry, and I'll just write down the answer: ac plus bd over the square root of a squared plus b squared, and then AD minus BC over the square root of a squared plus b squared. So the two vectors that we have to look at, let's call this V prime, and then we have W prime, and the area of the new parallelogram formed from V prime and W prime is the same as the original parallelogram. On the other hand, what's the determinant of the matrix given by V prime and W prime? Well, that's the determinant of the matrix, square root of a squared plus b squared, 0, ac plus bd over the square root of a squared plus b squared, and then ad minus bc over the square root of a squared plus b squared. And then since this entry is 0 in the lower left-hand corner, the determinant is the product of the diagonal entries, and that's AD minus BC. So the determinant is unchanged, as we see. On the other hand, since the vectors V prime and W prime are such that V prime sits along the x-axis and W prime is pointing in this direction, we know the area of the parallelogram is given by the absolute value of that determinant that we just computed. So the area of this parallelogram, which is the same as the area of the original parallelogram, is the same, AD minus BC. And that's the sketch of the argument in general. Okay, so that's the first part of what I wanted to say, but let's do an example. In order to do an example, I have to clear the screen. Okay, so here is an example. Let's find the area of the triangle in R2 whose vertices, let's say the vertices are 1, 1, 2, 3, and 3, 3. You can take any 3 points to do an example like this. Okay, so what does that say? So 1, 1 is here. 2, 3 is somewhere up here. And 3, 3 is somewhere over here. So we get this triangle, and we want to know the area. Well, we can double up the triangle to get a parallelogram. So the area of the triangle is 1/2 the area of the parallelogram, where we use these vectors v and w. So this is v and this is w. So what is v? V is the vector from pointing from 1, 1 to 3, 3. So that's the vector 2, 2, and w is the vector pointing from 1, 1 to 2, 3, which is 2 minus 1 is 1, and then 3 minus 1 is 2. So we need to compute the area of the parallelogram determined by those vectors. So we're going to compute the determinant and take the absolute value. So the determinant of 2, 2, 1, 2 is 4 minus 2, which is 2, which is already positive. So that's the area of the parallelogram. So now all we got to do is take 1/2 of that. So the area of the triangle in question is 2 over 2, which is 1. Okay, so that's pretty simple. Okay, so the next thing I want to do is consider 3 dimensions. And the thing which corresponds to a parallelogram in 3 dimensions is called the parallelepiped. If you had Math 2030, you would have seen that. So let me clear the screen. So volume of a parallelepiped. Okay, so what's a parallelepiped? You have 3 vectors in R3. And let's say V, W, and, oh, I don't know, P. So here's V. We put them together so that they're all at the origin. Their tails are at the origin. Here's W, and here's P. And now you form the solid determined by these three vectors. And you get a solid. It's a bad picture, but it's a box, each side of which is a parallelogram. And the statement is that if V equals A1, A2, A3, W is B1, B2, B3, and P is C1, C2, C3, then the volume of the parallelepiped determined by these vectors is given by the determinant, well, the absolute value of the determinant of a 3x3 matrix, the one that's formed by the 3 vectors, A1, A2, A3, B1, B2, B3, C1, C2, C3. And as you can imagine, proving this is not so immediately easy. What you would have to do ultimately in the general case is form a rotation in 3 dimensions so that one of the faces of the parallelepiped is sitting in the XY plane where the first vector is on the x-axis. And then you can actually see why this is true, this statement in that case. I'm not going to prove this formula, but it's true. What I'm going to do is just a simple example. Compute the volume of the parallelepiped formed by the vectors 1, 0, 1, 0, 1, 2, and 1, minus 1, 1. So the solution is very simple. You got 1, 0, 1, 0, 1, 2, 1 minus 1, 1. We're going to compute its determinant and then takes the absolute value. So let's use the cofactor expansion along the first row. So that's 1 times the determinant of 1 minus 1, oops, 2, 1, minus 0 times the determinant of 0 minus 1, 1, 1, plus 1 times the determinant of the 2 by 2 matrix 0, 1, 1, 2. And what do you get? You're going to get from the first calculation 1 plus 2 is 3 minus 0. And then it looks like a minus 1, so you're going to get a 2. So the volume is 2. Okay, so that's all I wanted to say about the last part of chapter 3. We're done with chapter 3 as of this short mini lecture. Okay, take care.